Good afternoon, everybody. I know we don't have the full complement yet, but we need to use every minute to make sure we get in all the stuff we need to talk about. So the game plan for today is we're going to go through some practice problems. I'll also introduce a little bit of material that we didn't cover with Chapter 3, but it's going to be pretty problem-solving heavy for Chapter 3 to help prepare you for the exam. Then we'll move on to Chapter 4. We'll try to have a little bit of a break, and I'll also let you know what topics in Chapter 4 you're still responsible for that I'm not specifically covering in the lecture today. So watching those lecture videos for Chapter 4 is going to be key. I will not be covering every single detail because some of those sections from Chapter 4 are pretty self-explanatory. Your exam will be available today at 5 o'clock. Let me write that down. I'll bring it up again. But exam 1, go to course content, then the exam 1 folder. And you'll see it there at 5 o'clock. You'll also see the metric system, the prefixes, and the reference sheet. Make sure that you print those off or you write them out and have them available during the exam. It requires lockdown browser. And it's available today, which is February 25th, through Saturday, the 27th, so make sure that you take that exam in that window. I'll bring it up again at the end of class to make sure that everybody gets it. And I'll send out an announcement to say, hey, exam is live. You should take it. It's a good idea. Any last minute questions before we get started with Chapter 3? I'm going to take that as a no. If you think of anything related to the exam or what have you, just go ahead and throw it in the chat or raise your hand and I'll address your question. So I went through the Mastering Chemistry Chapter 3 homework and quiz to see which questions were missed the most often. And so I pulled those out and we're going to kind of go over those as a way to fill in the missing pieces of Chapter 3. This first question is an energy conversion problem, which you should have been able to do. But I think that realizing that it was an energy conversion problem and that you needed to, look up an equality is probably where folks went wrong. So you have a sample of vegetable oil that you place in a calorimeter. And a calorimeter is just a tank inside of a tank that has a coil that you can burn samples, and all that energy that's released from burning a sample is absorbed by the water, and you can see a temperature change. From there, you can calculate how much energy is stored in food, let's say. So for this, we have a sample of vegetable oil, and when it's burned, it gives off 17.6 kilojoules of energy. What's the energy value in kcals per gram for the oil? And you have to express your answer with two significant figures. So let's highlight some things that are important. We have the 0.55 gram sample. We've got the 17.6 kilojoules. we know that our answer has to be in kcals per gram and 2 Sig Figs. So those are the important bits. Oops. So we need to express something in kcal per gram. What we have is kilojoules. And a mass. Kilojoules is another unit of energy. So we need to convert between the two. That means we need to use an equality. So the first step to our problem is to convert kilojoules to kilocalories. This is something that you'll be given. I will give you, on the equation sheet, you'll see the equality that you'll need to use. That's the equality that you need. Let me know if you're with me, because I know a lot of people are kind of just signing on, trying to get settled. So for those of you who kind of saw the beginning of this problem, let me know. Are we okay so far with just our plan of what we need to do? Okay. Okay. Thank you. So we've got our equality here. We've got to write conversion factors. Those are the fractions. 1 kcal over 4.184 kilojoules. And we have the kilojoules over 1 kcal. If I want to set up an equation to get rid of kilojoules and convert them to kcals, which of these conversion factors am I using, A or B? Exactly. I have to use A. That way, when I do the multiplication and division, I will cancel out kilojoules. But I'm not done yet. I do this conversion, but I still have to do the second step, which is to divide my energy by the mass, because the units that we have to report are kcals per gram. So how much energy is released for every 1 gram of vegetable oil that is burned? So to complete our equation, we're going to also divide that by the mass. That way our units are going to be kcal per gram. Does everybody see that step? Because the second step is key. And if you don't do that, then you're not going to get the right answer. In your calculator, what you're writing, and I'll put this in a different color, is 17.6, and I would use parentheses here, divided by 4.184, and then divided by 0.55. So that's what you should put into your calculator. When you do that, you get a bunch of digits. But remember, we have to use two significant figures. So what would my answer be with two significant figures? Yes. So this is what your answer should have been. Now everybody got, different numbers, but this is the way that you solve this problem. Questions so far? If you're ready to move on, let me know. So we got a lot to cover. When you say which one to use, you mean the conversion factor? Yeah, so you want to choose the conversion factor that's going to cancel the units you don't want and leave you with the units you want. That means if you have units in the numerator that you want to cancel, you need to have the conversion factor with those same units in the denominator. It's the bottom. When you have one unit in the top and the same unit in the bottom, you can cancel them out. And then you're left with the unit that's on top. And in this case, that's kilocalories. And we chose that because the question is asking for the energy value in kcals per gram. Does that help? Yes, you will have that conversion. You do not need to memorize, kcals equals to how many joules. That'll be there. You're very welcome. Now we're going to move on to a couple of topics in Chapter 3, and we'll talk about them and do some problems, and I'll give you strategies for how to do them. So make sure that you take note not just of what the answer is, but the process. That's why I spend so much time on problem solving, because problem solving is a method. The answer is great, but if you don't have a method down that you can apply to new situations, you're going to be lost on the exam. Specific heat. Every substance has a different specific heat. In the definition of specific heat, you'll definitely need to know this. That's why I'm highlighting it here. It's the amount of heat that raises the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. You also need to recognize the units. The SI system, you're going to see joules per gram degree Celsius. The metric system, you'll see calorie per gram degree Celsius. The specific heat for water is given down here, and these will be provided as well on the equation sheet. In the metric system, you have 1 calorie per gram degree Celsius, because a calorie is the amount of energy needed to raise a gram of water by 1 degree Celsius. You also have the same value but in joules. This is where the equality comes from. 1 calorie is equal to 4.184 joules. I can add a prefix in front of it like I did before. As long as you're adding the same prefix on both sides. Okay. So that's our energy equality from the last problem. The way that you calculate specific heat is by taking the heat that is released and you divide it by the mass times the change in temperature. And that change in temperature has to be in degrees Celsius. Fahrenheit doesn't work here. It has to be degrees Celsius or Kelvin. But let's say that I wanted to solve for the heat. I know what my specific heat is, but I'm trying to have an idea of how much heat is going to be released if I burn a substance. Then I can rearrange this equation to solve for heat. To do that, you multiply both sides by the mass times the change in temperature. Exam opens today after class, and it will close Saturday, 11:59 p.m. So as long as you've started your exam by that time, you'll be fine. You'll be given the specific heat equation as well, but I'm not going to rearrange it for you. You need to know what you're solving for. So if you want to jot this one down on your equation sheet before you start your exam, go for the gold. As long as you have started Respondus and you've started the exam, you can write whatever you want on that equation sheet as long as you don't have your notes out. So if you know from memory, okay, I want to write this down, this down, this down, so I can refer to it, do it. So you can't bring a cheat sheet with you, but you can recreate it during the exam. Does everybody understand me? Because I'm trying to give you the best leg up that I can. And that is one of the biggest test taking tips that I can share with you, is to recreate your cheat sheet during the exam. Okay. So you may want to have this one on there. Can I move on from specific heat? So in chapter 3, we covered kind of a lot of things. We started with looking at states of matter and classifying matter, talking about the physical changes of state, so going from liquid to a solid or a solid to a gas, those kinds of things. We can represent a substance going through all of those changes of state on a heating curve. On a heating curve on the x-axis, you have heat that you're adding into the system. So let's say that we have ice, and that ice is at minus 40 degrees Celsius. That's super cold. It's solid, rock solid. As we heat that ice, the temperature is going to increase. So that's this first part here. That's an increase in temperature. Next, we see a plateau. We've reached 0 degrees, and that solid ice is now melting. That's a phase change. With our increase in temperature before, there was a slope. So if you remember, like y equals mx plus b, like that's what I think of when I hear line or a slope. So that is a sloped line showing that you're increasing the temperature, you're adding heat into the system, but there's no phase change going on. It's just the ice is getting warmer. Eventually, that ice will hit that melting point of 0 degrees Celsius, and you'll have a phase change from solid to liquid. You're still increasing the amount of heat, but you're not raising the temperature. All of that energy is going towards melting the ice. When we talk about melting, the energy required to do that is called the heat of fusion. Now, in this case, we're talking about water, but the term heat of fusion can be used for anything. But we're talking about melting ice. Once all of the ice is converted to liquid water, we're going to start increasing our temperature again because we're still applying heat. Increase in temperature. That's a slope. Once that water gets to 100 degrees, say you put that pot of water on to boil some pasta, or maybe you're making some rice or something, it starts to boil at 100 degrees Celsius, which is 212 degrees Fahrenheit. At that point in time, you have another phase change. What's going on at that phase change? When you're boiling, you're going from liquid to what? What phase are we going to if we're boiling? We're taking a liquid, yeah, making a gas. It's right there. Not trying to trick you. Make sure you know those terms. When you're having a phase change, again, you're adding heat, but you're not changing the temperature. All of that energy is going towards changing the liquid to a gas. So for boiling, we talk about the heat of vaporization. That's the energy required to convert a substance from liquid to gas. And we're always talking about water here. I'll give you some numbers. The heat of fusion for water, and you'll be provided with this, is 80 calories per gram, which is the same thing as 334 joules per gram. So for every 1 gram of water, you require 80 calories of energy, 80 calories of energy for ice, right? Because we're melting the ice to water. You need 80 calories per gram of ice to melt it. And we'll talk about the reverse of this in a second. But does this make sense? We're going to pause here. Talk to me. How are we doing? Do I need to repeat anything? Because if you don't get this, then we can't move on. Okay. From here, since we know how to calculate energy during a phase change, and we know how to calculate the energy associated with the change in temperature, for that, we use specific heat. So that's specific heat, SH. For a phase change, you're using the heat of fusion or vaporization. We can put together an equation that sums together all the energy you need to go from solid ice to gas. The first stage, where we're going from minus 40 degrees Celsius to 0 degrees Celsius, that's a change in temperature. So we're going to use our heat equation. And that equation is specific heat times the mass times the change in temperature. So everywhere that you see black on this graph, the equation you use, oops, I wrote a P instead of a T. The equation you use is this heat equation. Everywhere you see purple, that's the energy to change phase. You're going from a solid to a liquid or a liquid to a gas. And that's going to be the heat of fusion or vaporization times the mass. Now let's talk about an example. If I have 50 grams of ice at 0 degrees Celsius and it melts, which equation would I use? The change in energy or the energy to change phase? So you can put temp or phase. Which one would I use, the black or the purple? If I've got 50 grams of ice at 0 degrees and it's melting, I would use the one for a phase change. So that means it's melting. I'm going to use my heat of fusion. And the problem will sometimes be specific about, okay, in calories or joules or kilojoules. Right now, I just want you to get the concept. That means I'm taking my heat of fusion times 50 grams. Does that help to put it in perspective about how you can go about calculating energy? Because those of you who participated, you got it right. Now we're going to take all of this same information and apply it in the reverse direction. Oh, I lied. We're going to do a problem. So we're going to do a heat of vaporization problem. This was from your homework. You may have had different numbers, but the problem should look familiar to you. You've got the density of liquid oxygen at its boiling point. Let me switch to my highlighter here. Is 1.14 kilograms per liter. Heat of vaporization is 213 kilojoules per kilogram. We need to know energy in joules, how much would be absorbed by 2 liters of liquid oxygen. We've got an answer with 2 Sig Figs. So this is directly from your homework. So I use shorthand because vaporization is a long word. So I'll write heat and then vap as a subscript, and that means heat of vaporization. So you're given a density and a volume of gas, or it's liquid oxygen, excuse me. And you have the heat of vaporization. The connection that you need to make here is that you can use the density and the volume to get the mass. So the first step, we're going to calculate the mass of oxygen. Use that density as a conversion factor. Remember that you can read it like this. 1.14 kilograms is the mass of 1 liter of oxygen. That's what a density reads like. So that's the mass. The second part of our equation, which I'll put them both together at the end, is we have to take that mass and calculate the heat of vaporization, or the energy from the heat of vaporization. And our equation for that is just the heat of vaporization times the mass. So we take the mass that we're going to calculate. I don't think you can see that. We'll do red. We'll take that equation and put it in here. And then we also have to multiply by our heat of vaporization. There's one more step, and that is to make sure that we answer the question in joules. So if you stopped here, your answer would be in kilojoules, and that's not what was being asked. You need joules. You won't always need to do that step, but make sure that you look at the problem to see if you do. So I'll label these. That's the mass. There's the heat of vaporization. And then this converts kilojoules to joules. So I'm going to pause here, let you take a second to breathe, because I know that was a lot. Take a second, drink it in, and let me know what's going on. Do I need to re-explain something? Is it clear? If it's clear to you, go ahead and put it into your calculator and let me know what you get. If it's not, speak up. So I'll give you guys a minute to kind of think it over, and then I'll check in. The 1.14 is the density. So that was from the problem. The 2 liters was also from the problem. Just so that you can see where everything came from. This is just setting it up. We haven't gotten an answer yet. I have an answer. If anyone wants to share an answer, they can. But for the sake of time, I'll put up the answer that I got. So that's what your calculator is going to tell you. And I'll cancel out all these units so you can see. There's our liters that cancel. Our kilograms cancel. The kilojoules cancel, and we're left with joules. With 2 Sig Figs, though, we either write 490,000 joules. The 2 is on the outside because we're multiplying. That's the 2 liters, the volume of liquid oxygen that we started with. And we're converting that volume to a mass by using the density. So this combines 2 concepts, density, which we talked about in Chapter 2, and then heat of vaporization, which is a Chapter 3 concept. Let's do a little more practice, and then I think it'll make a little more sense the more that we do. But I want to make sure that we get through as much of this as we can so that we can also get through Chapter 4. So I'm going to stop here and ask y'all actually a question. Which one do you prioritize more? Taking our time through Chapter 3 or making sure that we touch all the topics that I have lined up for us in Chapter 4? You can let me know in the chat. Which one is more important to you? Chapter 3 problem solving or getting through Chapter 4 material? Because that's how I prioritize the time. If you choose Chapter 3, that means that you're going to be more on your own for Chapter 4. So let me know if you want to make sure we do it all, or if you want to spend more time on Chapter 3. We have a vote for get everywhere, so get all the way through. Okay. All right. Then that means we need to finish up with Chapter 3 by like 3 o'clock. I mean, no later than 3:15. So let's keep it pushing. Keep me honest. When it's 3 o'clock, be like, Dr. Hefner, give me that warning. Okay. Now let's do a heating curve problem. Okay, we're going to be doing, so the conversions and stuff will be kind of worked in. Yeah, you can one-on-one with me, even if it's just for a few minutes after class. We can try another problem or two. Okay. So, heating curve problem. Again, this is directly from Mastering Chemistry. So you may be like, that looks familiar. It should if you went through your homework. We've got an ice bag containing 314 grams of ice at 0 degrees used to treat sore muscles. When the bag was removed, the ice had melted and the liquid water had a temperature of 14.5 degrees Celsius. How many kilojoules of heat were absorbed? Express your answer to 3 significant figures and include the appropriate units. This is a heating curve problem. The way that I know that is because we're talking about starting with ice at 0 degrees. And we end up with water at 14.5 degrees Celsius. So you have to melt and you have to increase the temperature of the water to get it to 14.5 degrees Celsius. So when you see a problem like that where you see 2 different phases mentioned, like ice and water or steam and ice, anything like that, that means it's a heating curve problem, and you will have to use the equations for heat of vaporization or heat of fusion, or both, and specific heat. So lock that in. When you see two different phases mentioned in the problem, and you've got a mass, you've got some temperatures, that means you're going to have to do a heating curve or a cooling curve, which we'll cover soon. I recommend that you draw it out. We've got heat added on the x-axis and temperature in degrees Celsius on the y. If we're starting at 0, or I should actually put that as negative, just so that the graph is a little bit prettier. We're starting out at 0 degrees Celsius, and that is melting. Remember that 0 degrees Celsius is the melting point for ice. So I put that in purple because that's what we did for our phase changes when you look at the heating curve that we talked through a couple of slides ago. Then we have the water melting, and we'll say this is 14.5 degrees Celsius. So for this problem, to calculate the energy, we've got to take the energy for melting and add it to the energy to increase the temperature of the water. When we talk about the energy for a phase change, what are we using? There's a term. If you have it written down, look back real quick. There's a term we associate with the energy that we need to melt something. It's the heat of fusion. It's the heat of fusion. And you'll be provided with that. On your homework, it's assumed that you can refer to all the tables and whatnot. So the heat of fusion for water is 334 joules per gram. You take that and you multiply by the mass of the water, and that gives you how much energy. Next, we have to figure out how much energy for the increase in temperature. We said that this is a slope, right? And for all of the slopes that we see, we're going to use specific heat. Specific heat times the mass times the change in temperature. The specific heat of water will also be provided for you. You do not need to memorize the specific heat of any substance. This is equal to the total energy to go from that ice that's melting at 0 degrees to liquid water at 14.5 degrees Celsius. I'm going to pause here. How are we doing? I know I'm hitting you with a lot of math and we're going fast. What I'd recommend you do as a way to study and practice is to go through and change the numbers. So instead of 314 grams, you can write 50 grams or 90 grams, whatever. Change the temperature. 14.5 degrees, maybe it's 20.5. Just make sure that it's, beneath the boiling point of water. And then walk it through the same steps so that you're walking through a fresh problem, but you can still use all the language to be able to recognize it on an exam. Half the battle is knowing how to solve the problem. The other half is being able to read the question properly. To do that, you need to practice with questions that are similar to what you're going to get. That's why doing the homework and quizzes is so helpful, because it gives you the same kinds of verbiage you'll see on the exam. I'm dropping gold. I hope y'all get it. Okay. Now let's put some numbers to this. For the phase change, we use the heat of fusion, which is 334 joules for every 1 gram of water. And we multiply that by the mass, 314 grams. To that, we need to also calculate the energy to go from 0 degrees to 14.5 degrees. That's the specific heat of water multiplied by the mass multiplied by the change in temperature. So the difference between 0 degrees Celsius and 14.5 degrees Celsius is 14.5 degrees Celsius. So we end up with joules for our first part. And joules for the second part. When you're doing Sig Figs for this, you want to enter this part into your calculator and get a number. And use Sig Figs. So here we've got, that's from your calculator with 3 Sig Figs. When you do this side for your calculator, now I'm not going to be too concerned about so that 0 is significant here. I underlined it. Okay. And you add those together to get 124,000 joules. That's the total energy that you need. Once you get to the end, go back to the problem and make sure it's really the end. When you read the question, it asks for how many kilojoules of heat. My answer is in joules, so I need to convert that by dividing by 1,000. And that is my final answer. So this was a heating curve problem where we had to look at the phase change and the change in temperature and calculate the energy associated with both of them and add it together. Make sure that you draw this. Draw your own little chart so you can see which pieces you need to add together. So talk to me. How did this go? If you have questions, go ahead and ask them now. If you're like, I think with practice I could do it, let me know that too. If you're like, man, I don't know, I want to know that too. I think I have another problem like this, so hopefully that'll help. Low key, remember, there's only going to be like a couple of these questions on the exam. It's not a full exam of heating curves and specific heat. Not telling you to just be like, well, throw caution to the wind, it'll be all right. But it's not going to be a huge portion of your exam. So keep that in mind too. And it's multiple choice. So as long as you get in the ballpark with the right units, you can choose the right answer. All of those things will help you. I almost feel like it's sacrilege that I'm telling you these things, but I want you guys to do as well as you can. And I think we do you a disservice when we don't share test taking tips with you. How many questions? 30-ish. Each of the 4 exams during the semester are about 30 to 35 questions. So that's, and included in that, there's like 2 or 3 bonus questions. So I do not put a time limit on the exam, but you must finish it in one sitting. But typically, you should be able to take it in about an hour to an hour and a half. Okay. All right, let's keep it pushing. We talked about heating curves. Now we're going to talk about a cooling curve, which is pretty much the same. We're just going in a different direction. We're starting with steam. And it's really, really hot. We're cooling it down to 100 degrees Celsius. That's where condensation happens. Condensation is the opposite of boiling. And to calculate that phase change, we're still going to use the heat of vaporization. Once all of that steam has condensed to water, then that water will begin to cool. So you have a big temperature drop between the water that was just freshly condensed from the steam, that's 100 degrees, all the way down to freezing at 0 degrees Celsius. For that, we're going to use our heat equation with specific heat. Once that water gets down to 0 degrees, we have another phase change on our hands. That's where it will freeze to ice, and we have to use the heat of fusion. So to summarize, with our heat of vaporization and heat of fusion, if you are melting, my my hand just got away from me, y'all. I don't know what happened there. That's not even a word. Melting or freezing, you use the heat of fusion to calculate the energy. Boiling or condensing, use the heat of vaporization. How do we feel about the cooling curve? Does this make sense to you? It's the opposite of the heating curve, but we still use the same kinds of calculations. So talk to me. Are we ready to try a problem? Okay. Then we'll do a cooling curve problem for your homework. You've got a patient who arrives in the emergency room. They're caused by steam. Calculate the heat that is released when 10.2 grams of steam at 100 degrees Celsius hits the skin, condenses, and cools to body temperature of 37.0 degrees Celsius. I think screen sharing just decided to go away for a minute. So bear with me. So here we go. Always when you see different types of states of matter with all the, degrees and the mass, that's going to be a heating or a cooling problem. And in this one, we've got steam and we've got water. We're starting at the steam and it cools to body temperature after it condenses. Draw your curve so you know what you're dealing with. If we're starting with steam at 100 degrees Celsius, we're at the condensation point. Let me draw that in purple to keep consistent. So that's our condensation. Then that water will keep cooling all the way down to 37 degrees Celsius. Oh, question about the exam. It is multiple choice. All of your exams are multiple choice. Hopefully that'll help you out a little bit. So this is our chart. And on the x-axis, it's heat removed because you're releasing heat as you cool the steam to water, and then you cool that water down from 100 degrees Celsius to 37 degrees Celsius. Does everybody see how I got that from the problem? Because this is the biggest jump you have to make from a paragraph, which your exams aren't going to have paragraphs of text like this. It'll be fairly simple. But go from the words to translating into what do I need to do. So talk to me about that. Are you still with me? Good. If you're not, it's okay to let me know that too. And if you're like, man, I don't want to hold everybody back, you need to let me know and you need to reach out and get help. So if you don't feel comfortable putting it in the chat with everybody, you can send me a private chat message or you can send me a course message. Sure, I can go over how I got to this chart. Is that what your question is? To go over how I got to the chart? Okay. So in the problem, we know that somebody arrives to the emergency room with a burn caused by steam. I have to calculate the heat that's released when 10.2 grams of steam at 100 degrees Celsius hits the skin, condenses, and cools to body temperature. Because I see two different states of matter, I've got steam, and then I've got water, which it says that it condenses, which means you're making water. And it cools to body temperature. So I know I'm going from steam to water. And that water is at 37 degrees Celsius. So to get there, I have to first condense the steam at 100 degrees Celsius to water at 100 degrees Celsius. Then the water cools down from 100 degrees to 37 degrees. And that's what I have on the chart. The first one, ooh, can't see that. That's a little bit too dark. Trying to keep all the colors together. So the purple on the chart is for steam condensing to water at 100 degrees Celsius. That's what that purple line is. The black line is for the water cooling. Does that help? For time's sake, we got to keep pushing. For the total heat, we've got to use some kind of an equation to calculate the energy to condense and add that to the energy released to cool. For our phase change, we're always going to use heat of vaporization or heat of fusion. And that will be provided for you. In this case, it was provided in the problem. I'm going to use calories this time just to show you with the different unit. It's the same process. And on your homework, you could have done it with calories or joules, and it would have been fine as long as you had the right number of Sig Figs. So our heat of vaporization is 540 calories per gram. The mass was given in the problem as 10.2 grams. Whenever we're talking about a change in temperature, we use specific heat. The specific heat for water is 1 calorie per gram degree Celsius. Same thing as 4.184 joules per gram degree Celsius. Fill in the mass. And the temperature change, you just want to find the difference between 100 degrees and 37 degrees. You get a number here. And you get a number for the other part. And you add them together. When you add them together, that's what you get. Make sure that you double check and you look at the problem. Did I give my units right? And it says express the heat to 3 significant figures. We did that. And include appropriate units, which has to be units of energy. So calories or joules. That's it for heating curves and cooling curves. Does this help you feel a little bit better about those curve problems? My suggestion to you again is to take the problems that we did, change the numbers a little bit, and then write it out, walk it through yourself. That way you can replace it And you can kind of get, okay, so now I'm doing this, now I'm doing that, I'm calculating this energy, I'm calculating that energy. I'm using this equation because I'm calculating the amount of heat released when I'm cooling the water from 100 degrees to 25 degrees or something like that. Okay. Make sure that you're not just writing it down, but that you're understanding why you're using each equation and what each part of the equation means. Any final questions before we move on to chapter 4? Okay. So we're going to move on to chapter 4. Before we talk about material, I'm going to let you know what topics I'm not covering specifically in live lecture that you're still responsible for. Sections 4.1 and 4.2 are just introducing what's an element. Elements are, on the periodic table. They have 1 or 2 letter symbols. Pretty simple stuff that you don't need me to read to you. Section 4.3, there's a little bit of the history of the different models of the atom. I will cover some of that, but I'm not going to cover Dalton's atomic theory, and I'm not going to explicitly cover the plum pudding model from J.J. Thomson. So if you watch the videos, then these names and things should be familiar to you. If you did not, you will absolutely need to watch the pre-recorded videos for chapter 4, because this lecture is not enough in and of itself to give you all the information you need for your homework and quiz and for your eventual exam. So I'll fill in a good portion of 4.3. I'm also not going to cover the electromagnetic spectrum. So that's just talking about the different wavelengths of light, high energy, high frequency, low energy, low frequency, that kind of thing. Watch the video. These other 3 topics I'll kind of mention, but I'm not going to go into specific detail. I don't have slides on them in this lecture. So you'll need to get that from the video. I want to give you 5 minutes for break. So we'll break till 3:25. So you can kind of shake your brain out and like go, woo. And then we'll dive back in. But we won't be doing any math. So if math is like the boogeyman is going home for the rest of the day. Come back in 5 minutes. All right, everybody. We're going to get started again. And for those of you who may have signed out, there was a question in the chat for when does the test open. And the test opens today, pretty much right after class. So if you check at like 4:45 on Blackboard, you can take the exam right then and there. It'll be in the exam 1 folder. It's already there. It's just not available to you. So if you wanted to just take it right away, you could do that. Baby Hefner has made his, his usual appearance. So he'll be joining us. The exam closes on Saturday. Saturday at 11:59 p.m. So as long as you start it before Saturday at 11:59 p.m., you'll be good to go. And there is no time limit. I just ask that you complete the exam in 1 sitting. Other exam questions before we start chapter 4? Alrighty. Any other exam questions before we start chapter 4? Okay. If you think of anything, just let me know. So we're going to pick up on chapter 4 with a man named Ernest Rutherford. He used to work for J.J. Thomson in his lab, and then eventually got his own lab and his own students, and decided to test the model that J.J. Thomson came up with, which was the plum pudding model. The plum pudding model said, I have this sea of positive charge, and within that, I've got electrons, and the electrons are like the plums in the pudding. This meant that the atom is mostly empty space. Rutherford said, okay, that's great. We've got this model. I want to test it. So here's the hypothesis. If the plum pudding model is correct, I'll abbreviate that, then we should be able to pass these big particles through an atom, and all of the particles should just go straight through. So I can shoot particles at an atom, and they won't be deflected at all, because there's nothing there to deflect it. These particles are big, and there isn't anything massive enough in the atom to make those particles change direction. They're just going to go straight on through. The experiment is what's shown here. You have a source of alpha particles in a lead container, and you shoot a beam of those particles at a thin gold foil, which is why it's called the gold foil experiment, the thin foil experiment, something like that. And when those particles go through, then they're detected by a fluorescent screen. So if the particles go straight through versus being deflected at a large angle, you'll be able to detect that. The results, well, most of the particles went straight through undeflected. But some were deflected at large angles. So the conclusion that Rutherford came to was that there must be some kind of dense nucleus at the center of an atom. And that nucleus is comprised of protons, which are positively charged, and neutrons, which have no charge. They're neutral. I explained that in the video, but I wanted to break it down for you like this with the hypothesis, experiment, the results, and the conclusion so that you could put those things together and you can have it when you're answering questions. Baby Hefner is just not happy today. Any questions about the gold foil experiment? Okay. So these are the subatomic particles. I'm sure that at this point in time you're in college and you have probably seen protons, neutrons, and electrons at some point. You may not have seen the symbols for them, which are in this column. Make sure that you recognize those because they'll be used in your homework, the quiz, the exam, and throughout this lecture. So just take note of those. Then there's the charges, which we already kind of covered, protons and neutrons, and then electrons are negatively charged. The masses you do not need to memorize. Just know that protons and neutrons are about the same, and electrons are super duper tiny. So when we're talking about the mass of an atom, the majority of that comes from the protons and the neutrons in the nucleus. And the final column just says the location of these subatomic particles in the atom, whether it's in the nucleus or outside the nucleus. And the only thing outside the nucleus is the electrons. Let me know if we're good to move on from here. I think this is pretty much kind of common knowledge for you all at this level. Okay. So when I said there was no math, I lied a little bit. It's addition and subtraction. So nothing heavy duty. This slide showed up in the recorded video, and this is kind of my summary slide to get everyone to the same place. When talking about an atom of an element, we need to have some vocabulary. The atomic number is going to tell you the number of protons. And the atomic number is why each element is unique, because there's a different number of protons. And those protons and neutrons in the nucleus, that gives each element its specific characteristics, like being a metal or a non-metal. You know, whether it's malleable or brittle. All those kinds of things come from just the structure of the atoms of that element. Then we have the mass number. Think about that as the total number of particles in the nucleus. That's going to be the sum of the number of protons and the number of neutrons. If you need to figure out how many neutrons are in a specific isotope of an atom, then you take the mass number and subtract the atomic number. Please note, mass numbers are only given for specific isotopes. You're not going to see the mass number on a periodic table. So when we're talking about an isotope, we're talking about two atoms of the same element that just have different neutrons. I'll give you an example. let's say that we have carbon, and if you have your periodic table, this would be a good time to pull it out or pull it up on Blackboard. So pull that out. If you have your periodic table, look up carbon. The symbol for carbon is a capital C. Once you find that, you'll see two numbers, a whole number and you'll see a decimal number. That whole number is the atomic number. In the chat, I want you to put what the atomic number is for carbon. Six. The atomic number is 6. One more minute, y'all. Okay. Baby Hefner is trying to get famous, y'all. So we said that carbon has a symbol C. Its atomic number is 6, and that atomic number is usually above the symbol. It'll be directly above or maybe off to one side. And underneath that, you'll see a decimal number. We'll talk about that decimal number in a minute. Now let's say that I have 2 carbon atoms. Okay. I have a question. You didn't miss anything. We're getting there. You didn't miss anything. The atomic number is on the periodic table, but you can't figure out the mass number unless you know something about the number of neutrons. Or if you know the mass number, you could figure out the neutrons by subtracting the number of protons. But we're going to do a little bit of practice for that. But I want to give you an example of what an isotope is. If we have 2 carbon atoms, and one of them has 6 protons and 6 neutrons, and the other one has 6 protons and 7 neutrons, those are 2 different isotopes. This is carbon 12, which this 12 is the mass number, versus carbon 13. Same element, the only difference is the number of neutrons. 6 versus 7. Does that concept make sense? We just went over kind of what an isotope is, and then also the mass number. So if you're good, let me know. If you're not good, let me know. We won't have all the time in the world, but I at least want to know. Okay. Yeah. So we'll take a little time to fill in a couple of rows of this table. We're going to use the periodic table. And if you don't have one, I'll kind of help you along a little bit, to identify each element and write its atomic symbol. The atomic symbol is just the symbol of the element with the mass number at the top and the atomic number at the bottom. So if we use our carbon example, carbon 13 would have a C, and then at the top it would be a 13. Underneath that 13 would be a 6. That's the atomic symbol. For this first row, we know the atomic number is equal to 9. Since we know the atomic number is equal to the number of protons, we can also fill in the number of protons. The mass number is the protons plus the neutrons. So we take our 9, and we've already been provided with the number of neutrons, that's 10, for a mass number of 19. The last piece is the number of electrons. And we're dealing with neutral atoms, which means that these atoms don't have any charge. The number of protons in that atom is equal to the number of electrons. So if I have 9 protons in my atom, I have 9 electrons, so that they cancel out. We've got positive 9 from the protons, negative 9 charge from the electrons. You add those two together, that gives you 0. The last piece is figuring out which element. The atomic number you can look up on the periodic table. So you find the element that has a 9 above it, and that element is fluorine. To put this in the proper atomic notation, you write the mass number up top, which was 19, and the atomic number below that. I'll walk you through one more row before we move on, so you can fill in this last row as practice. The number of protons in a neutral atom is the same as the number of electrons in a neutral atom. So if you know this, the number of protons, then you can fill in the same number. So let's do the second one. This time we've got a mass number and the number of protons. Automatically, since we know the number of protons, we know the atomic number. To figure out the number of neutrons, we can take that mass number and subtract the number of protons to get the neutrons, because mass number is protons plus neutrons. You do that math and you have 16 neutrons. The number of electrons, again, is the same as the number of protons in a neutral atom. So 15 protons means 15 electrons. To figure out the identity of the element, you need to look up the element that has a 15 for its atomic number. If you have a periodic table, find it and tell me what the symbol is for that element. That symbol you're looking for is a P for phosphorus. And that's the atomic notation there. I'm going to leave this last row blank for you to try on your own. Hopefully the work up here will help you be able to fill it in. So we've covered atomic number, we've covered mass number, but we haven't covered atomic mass. And that's the other number that you see on the periodic table. It's the decimal number. The atomic mass is calculated as a weighted average. So it takes into account not just what the mass is of all the different isotopes, but how much of that particular element is made of which naturally occurring isotope. In our example, we've got chlorine. There are two naturally occurring isotopes. We've got chlorine 35 and 75.76% of all the chlorine on the Earth, in the atmosphere, is chlorine 35. It's that isotope. The remaining chlorine is chlorine 37. You only see one number for the atomic mass, and that is the weighted average. What that looks like is you take the mass of each individual isotope, which I listed here, and you multiply it by the percent abundance. That AMU stands for atomic mass units, and that's what we use when we're talking about the mass of an atom because it's so small. You take that mass and you multiply by the percent abundance, which, remember, we can write percentages as a fraction. So if we took that 75.76%, we could write that as 75.76 over 100. We add that to the 36.965 multiplied by the percent abundance. So this is chlorine 35. And this is chlorine 37, their respective contributions. And if you did that math, you would end up with 35.45. Let me know if that concept makes sense. I have an example, but if you guys are good with this, then I'd rather skip that example and move on to the next topic. I'll fill in the problem for you after class, but if you're okay with the idea of atomic mass, I'd like to move on from it. So let me know. Be honest, but let me know. We got to vote for move on. So I will complete this problem and have it in the notes. Now we're getting to the part that's a little bit more abstract. We're going to be talking about the different energy levels within an atom so we can talk about where electrons are within an atom. We just said that atoms are largely empty space. You got this nucleus with all the electrons hanging out on the outside of the nucleus. but they're organized. They're in energy levels. In the pre-recorded video, I talked about atomic spectra, which is just if you take an element and you heat it up and it's a gas, you get it super excited and those electrons will get excited, right? They absorb energy. You stop exciting those electrons, eventually they'll release energy and fall back down to ground state. The energy that's released, well, light is a wave as well as a particle. So you can see the light that's emitted, and there's distinct colors emitted for each element. It's kind of like an atomic fingerprint. The atomic spectra for each element is the evidence for different energy levels. In an atom, we're talking about a specific energy at a specific energy level. And we call those principal quantum numbers. Okay? I may also call it a main energy level. You'll also see this referred to as N. So N equals 1 means main energy level 1, or principal quantum number 1. As you increase the N, that main energy level, you increase the energy, and the electrons are farther away from the nucleus. So if this is our nucleus, and we've got N equals 1, that's kind of close to that nucleus. N equals 2, and N equals 3. Electrons that are hanging out in N equals 3 are much further away from the nucleus than the N equals 1 electrons. But in that space in between, there's no electrons here. It's just in those black bands. Those are the energy levels. So you've got electrons here in this kind of sphere and here, but nothing in between the two. There is no N equals 1.5 or 1.7. You're either in N equals 1 or N equals 2. And this concept of there being no in between, but specific discrete energy levels, that's called quantized. The energy levels are quantized. And the example I use is stairs. You can't walk up half a stair. You will look silly trying. If you don't put your foot up high enough, you won't get onto that stair. So you're only on stair 1 or stair 2. There is no stair 1.5 unless you can levitate. And if you can, I'm interested. So talk to me about energy levels. We may not have the time to go through and redo the whole slide, but at least let me know where you are, because we may be able to shore some of this up next week when we do chapter 5. So are we good on energy levels, or is it kind of meh? Yes, they are. Atoms are a lot. Good thing this ain't on the exam. Chapter 5, we're going to talk more about atoms and nuclear energy. So we'll kind of be talking about this stuff again. And I'll make sure that we do a couple of problems together. Okay. It's a very abstract concept, so it's hard to wrap your mind around. I understand that. I've been doing this for years. So, and sometimes I'm still like, wait, what? Oh, yeah, that's right. So, it's when you're dealing with something that's so small, and I like this. Well, this isn't specifically what I do. I'm a biochemist. So, I care about the chemistry of biological beings. So there's more context and more reason behind studying things than just very abstract concepts. But you have to get through this to get to the fun stuff. Yeah, it's a lot better. I promise. So we know that electrons occupy specific energy levels. And all of the electrons that have the same energy are going to be in the same group. So if you think about going to the library, all the books are organized according to the Dewey Decimal System, which is kind of alphabetical. And when you look at the shelves, you're going to find, you know, if it's got this number to this number, it's on shelf 1, shelf 2, shelf 3. It's the same thing with the energies. If you have energy equals X, then those electrons are going to be in N equals 1. If you have more energy, energy equals Y, then you are in energy level 2. And again, the higher N value indicates higher energy, and those electrons are going to be farther away from the nucleus. Now we've got more than just the main energy levels. We also have sublevels. Those come in the flavor of S, P, D, and F sublevels. So let's say it's post-COVID times. You go on down to Charlotte because you want to go to that big old mall. And you're like, I need to park. But I don't want to leave my car just out there in the parking lot. I'm going to park in the parking deck because the sun is going to destroy the paint on my vehicle. When you go into that parking deck, there's different levels, right? You can be on first, second, third, whatever. Those levels, those big levels, that's the main energy level. So that's like the first floor of a parking deck, let's say. Some of those parking decks are so big that they have like 1A and 1B. You know, which side of the parking deck are you on? That's going to be like a sublevel. So you get a little bit closer in on where those electrons are. And each main energy level has a certain number of sublevels associated with it. Once we get down to the number of orbitals, which is shown here in all of these little squares, the orbitals are like parking spaces. And sometimes in some parking decks, they're numbered. So you know that your car is in space 233. So you've got the main first floor. You parked in A, and your space number 233. That's your N equals 1, let's say. That is the S sublevel. And you are in the 1s orbital. That's how you can make that analogy work. So we've got energy levels, the whole floor of the parking deck, the sublevel, A or B, which side are you on in the parking deck? And then we've got the orbitals. And there's different numbers of orbitals for the different sublevel types. But let me know if that analogy helps a little bit. It may still be like, I'm going to forget this as soon as we end class. That's okay. You'll need to go back to this chapter and review it and try some problems. But let me know if the parking deck analogy, if that's something that you might be able to use when we're not in class together. Okay. So each of these sublevels has a certain number of orbitals associated with it. S sublevel, 1 orbital. The P has 3 orbitals. The D has 5. And the F has 7. That's something you will simply have to commit to memory. There's no rhyme or reason that you'll be able to figure out how many orbitals are in each of these sublevels without a whole bunch of math and understanding, okay? So commit this to memory. Before we can talk about how to fill these orbitals and all these sublevels with electrons, we've got to talk about the Pauli exclusion principle. Each orbital can hold a maximum of 2 electrons. And the electrons in the same orbital are going to repel each other. Remember, they're both negatively charged, and like charges repel. So if they're going to occupy the same orbital, then they must have opposite spins. And the way you represent that is using an arrow up and an arrow down. That represents opposite spins. In the video, I talk about how if you ever had to share a bed with one of your cousins or somebody, a bunch of people in town, and ain't nobody got no money for no hotel, then one person sleeps the right way, the other person has their head at the foot of the bed. That's electrons. Okay, they don't want to do that. So they will spread out as much as possible. But if they have to, they will share. So let's put that together, okay? What we're leading up to is writing electron configurations, but we're going to ease on into it by drawing an orbital diagram. So an orbital diagram, I use lines, but sometimes you'll see boxes. Doesn't matter. Each line represents an orbital. So there's a sublevel. We got sublevels on the bottom. Each line is equal to 1 orbital and holds up to 2 electrons. If we want to draw a diagram for neon, neon has 10 electrons. We know this because if you look at the periodic table, its atomic number is 10. That means it's got 10 protons. So it has 10 electrons in a neutral atom. We need to place 10 electrons. You fill the sublevels from the lowest energy to the highest energy, and that's how they're arranged. We need to place 10. We completely fill the 1s sublevel. It can only hold 2 electrons because there's 1 orbital there, and each orbital contains 2. That means we've got 8 more electrons to place. The next sublevel is the 2s. We completely fill that. Now we've got 4 electrons placed, but we still have 6 more to go. This is where you want to watch. I'm first going to fill each of the orbitals with 1 electron, and they all have the same spin. Those electrons are trying to spread out. So there's 3 electron siblings. They each have their own beds. But then your Aunt Carolyn comes into town, and your Aunt Karen comes into town, and you know one of your cousins has a baby. All of them gonna need a bed. So you double up. There's all your cousins. So we did the 3 electrons first with the same spin. Then we added on the next 3 with the opposite spin. And that gives us 10 electrons total. Let me know how we're doing. If it's, I need practice, that's fine. If it's, child, you lost me, that's fine too. I need to know so that next week we can try to pull some of this stuff in as we're doing chapter 5. So it's really critical that you let me know the areas that you need to address again next week so I can do that for you. Hang on for another 15 minutes. Even if you just let me know, I'm still here, Dr. Hefner. That's fine too. So there's 3 arrows because there are 3 p orbitals, okay? And each of those orbitals can hold a total of 6, or a total of 2 electrons. So we first went through and filled each orbital with 1 electron in the same, having the same spin. So that's the black. But we still had 3 more electrons to place for neon because it has a total of 10. If we just stopped with all the black arrows, we would have 7 electrons. That's not neon. So we add another 3 electrons in the opposite spin to completely fill each of the 2p orbitals. Now each of those orbitals has a maximum of 2 electrons. Does that help? I'll try to work in some practice next week. I at least want to touch on all the things so that it won't be completely and totally foreign to you next week. So I'm going to skip over this example. We'll do this next week. Right now, it's kind of the showcase. So we'll do some more of that next week. I do, however, want to get to writing electron configurations. So I'm going to make a cheat sheet for you here. You'll want to either make your own now along with me, or make it later, print it off from the notes, whatever it is, make sure that you have one for yourself. I'm going to highlight and draw some things, and it will help with writing all of these configurations. We talked about the different sublevels. Everything in black is filling an S sublevel. So any electrons, the electrons at the end of that configuration are going to be in the S sublevel. That'll make a little more sense as we go along. Then we've got the P's. Next, we've got the D's. And finally, we have F, which is down at the bottom. This table down at the bottom fills in here. So after barium, you go down here to this row, and then you come back up to the main table. Those main energy levels that we were talking about, n equals 1, n equals 2, the parking lot level, that's the row. Okay, so the period on the periodic table corresponds with the n. So the first row is n equals 1, second is n equals 2, all the way to 7. So if I were looking at lithium, the outermost electrons in lithium are going to be in the 2s. Everything up before that is full. And again, that'll make a little more sense as we write these configurations. I'll fill in the rest of the numbers for you. This is your cheat sheet for writing electron configurations. In the video, I go through and write out the full order from the lowest energy level to the highest. I'm not going to do that here, but that would be a good thing to add to this periodic table. Make sure that you have something like this in your notebook. It will help you when you're doing homework and quizzes. I'll show you how to use it. Let's say that we want to write a configuration for oxygen. This is oxygen right here. I have to fill all of the sublevels until I get to oxygen. So I'm going to walk along the periodic table and fill in the electrons. You start with the 1s. That is the lowest energy sublevel. you write the number of electrons as a superscript. So that's a number above a letter like that. How did I get the 2? Because this is the 1s, and I've got 1, 2 in the row that are in the 1s. After that, you drop down to the second row because that's only 2 electrons, and we haven't hit oxygen yet. So now we're in the 2s, and there's 1, 2 spaces here. Neither one of those is oxygen, so I fill the 2s completely. Now we're in the 2p. So we just walked across, n equals 2. We're on the right hand side of the table, and this is where oxygen lives. We have 1, 2, 3, 4, and now we're at oxygen. The total number of electrons should be 8. If you add up the superscripts, 2 plus 2 plus 4 gives you 8 electrons. That's how you write the full electron configuration for an element. I'm going to show you another example, and I'll introduce the abbreviated configuration. So we're going to write this for neon. This is going to be the full configuration for neon. We talked about neon before. It has 10 electrons. We're going to start with the 1s. Because it's the lowest in energy. And we're going to fill it because there's only 2 spaces in the 1s, and we've got 10 electrons. Moving on to the 2s. We're going to fill both of those spaces because we're not at neon yet. We go across to the 2p. Neon is in the 2p neighborhood, so we count. That's the configuration for neon. Neon is a noble gas, which means that it has what's called a full octet. The n equals 2 sublevel holds the maximum number of electrons it can hold. Okay, it's full. That's what we mean by a full octet. That n equals 2, we've got the 2 sublevels, the s and the p. Both of those sublevels are holding the maximum number of electrons that they can hold. When you're at that point, you're in this column on the far right, and these are noble gases. One more thing, and then we're going to end class. Let's say I want to write something for phosphorus. I can use the same idea, starting with the 1s, and then I go to the 2s. This one's a bit longer, so I've got to go 2p. That's completely full. Now I'm at the 3s. Oh, man. So orange is the 3s. And then I have to do the 3p. And I count because that's the neighborhood that phosphorus is in. And I get this long configuration. But what if I wanted to write an abbreviated form? We just did a configuration for neon. What I just put in a bracket, that's the configuration for neon. So I can represent all of that with neon in a bracket. Then I can take my remainder and add it on. That is the abbreviated form. So we didn't finish 100% with chapter 4. We'll finish it up next week. So I'll continue to give extensions as necessary until we sync back up with our chapters and our homework. We lost time because we didn't have last week, and chapter 4 is really supposed to be covered over 2 weeks. So I will push back the due date for the homework. Don't worry about it. I suggest you look at it, you start working on it, and bring your questions to office hours next week. So let's skip ahead to reminders. So we're not going to have the chapter 4 homework and quiz due on Wednesday. I'm going to push that back to Sunday. So not Sunday this week, but Sunday next week. Come to office hours Tuesday, 11:30 to 1. Or you can set up an appointment using course messages. Chapter 4 is really abstract, and writing those electron configurations and understanding the different terms and how they relate to each other can be more than a notion. So please reach out. And of course, after all this, you're going to want to know about your exam, right? Because who wouldn't want to take an exam right now? Your brain is completely mush, and you're like, chemistry, why do I care? Why should I do it? I'm just going to go sell pretzels. Don't. Talk to me, okay? Your exam is available. It will be available once we close out a class and I make it available. We'll say 5 o'clock, so go shake your brain out, and then you can come back and take your exam if you want. It will be available until Saturday at 11:59 p.m. You have to use Lockdown Browser and Monitor. That was in the syllabus. We already talked about it. So if you have a Chromebook, you cannot use Lockdown Browser and Monitor. So you have a little time to borrow a laptop from the library, take it on campus, use a family member or a friend's computer, something like that, as long as you're safe. But you cannot use a Chromebook. It's multiple choice, about 30-ish questions. Should take you about an hour and a half. Send me a message if you have questions. I'll try to check my messages a little more frequently between now and the time that the exam closes. No promises, but I will try. It's 4:30. If you don't have any questions, you're free to go. Otherwise, stick around and ask your questions.